Okay, it's 8:30, so let's go ahead and get started today. So good morning, everybody. Hope everyone had a really good weekend. Um, I know it's still virtual, so hopefully everyone had a good weekend, staying safe in their homes, right? Okay. So some announcements. So I posted the first homework. So I saw that the Discord server was kind of busy over the weekend, so it seemed like people were working on the homeworks. Are there any questions on the homework that I can answer before we get started for today? Okay, go ahead, shoot. How do you do problem 3? Okay, let's go take a look at problem 3, and then maybe I can do one together with you guys. Okay, so problem three kind of is pertaining to basically what we covered at the end of lecture last week. So remember, this has to do with the fact that every fluid flow situation you come across can always be described by 1, its characteristic size, 2, its characteristic speed, and 3, its characteristic pressure. So basically what I want you to do with this problem is to take those situations that I've listed, situations A, B, C, D, and E, you can choose your own, and I want you to describe it, okay? According to those 3 characteristics, and also I want you to draw a sketch. Okay? So if we take, part A, so let's do 3A, okay? So part 3A asks you to describe the flow of oil in the Trans-Alaska Pipeline. Okay. And so the Trans-Alaska Pipeline, if you just do kind of a Google search, is basically the main way that oil is transported from Alaska down to the rest of North America, right? So it's a big pipe of oil, basically. Okay. And so, first thing is we have to draw it. So let's go ahead and draw a gigantic pipe of oil. Okay. Right. So that's my way to do it, because I'm an engineer and I don't really have much artistic skill, but you can see, if you can imagine, this is kind of like a cross section of the pipe. If you can draw a better pipe than me, that's definitely encouraged. This is kind of like the bare minimum, even maybe like one level below the bare minimum of what I want for this. Right? Okay, so that's the characteristic, or that's the sketch. So now let's do the characteristic size. So basically, for a lot of these problems, I want you to look things up on Google as to, what these could be. So if you just Google, like, Trans-Alaska Pipeline, and then they'll give you a lot of statistics, like how big the pipe is, how fast the oil flows in it, what's the driving pressure for all those things. So you're gonna have to do a little bit of research on your own. So I'm not gonna do everything for you here, but if we just search, let's see, Trans-Alaska Pipeline. And let's do size. Okay. So if you just do a quick Google search of Trans-Alaska Pipeline size, you'll see that the first thing that Google tells you is that the diameter of this pipe is 48 inches. Okay. Right. And so for part 2, you can, where it asks you for a characteristic size, you can say the diameter is 48 inches. Okay. Okay. And then you would do the similar thing for part 3 and part 4, where I want you to look up, just do a bit of research. How fast does the oil flow in this pipeline, and what kind of pressure does it is it exhibited to? So for the pressure, you might you might have to do a bit of digging for that. But one thing that might help you is if you search for like driving pressure. Okay. Another thing you might search up is head pressure. Okay. So problem 3 is mostly just a fun problem. So I just want you to basically look up some things on Google and just list some stats. Just to give, this is mostly just to give you a sense of, you know, all the different kinds of fluid flow there are out there. So I purposely chose some that are like, you know, you have oil flow in a pipeline, you know, 48 inches is pretty big. You know, and if you look up the length of this pipeline, it's even bigger. But then you contrast that with like part B, where, you know, blood flow in your aorta, that's a really, really small, relatively small, you know, fluid flow. Next, you have part C, which is weather patterns, which are probably, you know, some of the biggest fluid flows you'll see, at least on Earth. And then part D is something that's really small too. So you have something that's in your drinking fountain. So, you know, it's, you know, it's not something I'm really checking for correctness, because I know, you know, even when you look stuff up, some of these numbers will vary a bit. But I just want you to get into the habit of, you know, if you have a fluid flow situation, you know, how big is it? How fast is the fluid flowing? And what kind of pressure is it? Okay. Does that make problem 3 make a little bit more sense? Great. Okay. So then there's also a question on problem 2C. I think, yeah, that one's the one with all the partial derivatives. Okay. So problem 2, I want you guys, this is just practice on, you know, making sure all these quantities are dimensionally homogeneous. And so all of these are actually real fluid mechanics equations. Some of them I modified just to make sure that they're wrong, but, you know, all of these are actual fluid mechanics. So 2C, that's going to be a really important equation later. So that's called the Navier-Stokes equations, which is as close as you can get to like a master equation in fluids, which is, you know, rare. Right? So so let's do some partial derivatives. So so I know the partial derivatives make things a little bit confusing, but let's walk through just a couple of them. Okay. Okay. So the first term that we have here in Navier-Stokes is partial u, partial t. So it's the partial derivative of u, where u is the velocity and t is time. Okay. And so the way that you you find the dimensions for these partial derivative terms is you basically just ignore the partials. So the partials are just, they're just kind of there just to let you know that it's a derivative. But in terms of dimensions, you can just look at just the physical quantities. So it's just the physical quantities. In here we have a velocity. So velocity is length over time. Okay. And on the bottom we just have time. So it's just time. So we have length over time squared. Okay. So you basically just ignore the partials, and then you just find the dimensions from that. So I think that should get you, that should be good for the second and the third terms. But then let's do the last term, because the last term is a little bit tricky because you have you know, a second order derivative. Okay. And so just like we did up there, we're going to ignore the partials. Okay. So up top we just have a velocity. And on the bottom we have x. So x here is a length, has the units of length basically. Okay. But you know, you can see here that on the bottom we have dx squared. Okay. So we need to add a squared here. Okay. There's a squared on top, but you can see that the squared on top acts on the partial. So we're just going to ignore that. So it's the way you kind of read this kind of in words, you say d squared u over dx squared. And so since the u is not squared on top, we just leave it alone. But then since the x on the bottom is squared, we have that one squared. So in the end, this quantity, and then there's also the viscosity in front of this. So you need to take that into account. But just this term by itself has dimensions of 1 over, because this is going to cancel with this, L times T. Okay. Right. So hopefully that helps you guys out. And then you know, there's two other, well, we did like 1.5 terms here. So make sure you kind of use the same technique for the rest of the terms. Okay. Does that make a little bit more sense for that one?
Yeah.
Okay, great. Are there any more questions on this, or just any other questions about the class before we get started for today? Okay. So I want to thank everyone that filled out the minute papers at the end of last week. So you know, it's kind of as I predicted. You know, I got a lot less draw on it than you know, if I did it kind of in person. But you know, the ones that did fill it out, you know, thank you very much. You know, that information was always going to be valuable. I know the first week it's a little bit hard just because, you know, we didn't really go over too much, but I think going forward it's something that's going to be really valuable for me, and hopefully it's, you know, something that helps you kind of recall, you know, whatever stuff we went over this week too. Okay, so let's get started on the topic for this week. So this is something that we're going to be covering for the next 2 weeks, because there's kind of a lot to cover in it, and that's fluid statics or hydrostatics if you're talking just about water in particular. Okay. And so the key word in this topic is statics. So if you go back to, you know, your understanding of statics from solid mechanics, statics is something that doesn't move. It's just something that's in kind of static equilibrium. That's what we say. So this is the same thing. So fluid statics is basically the study of fluids that don't move. Okay. Okay. And so, you know, the old saying that, you know, you have to learn to walk before you can run. But in this case, you know, we have to learn to stand still before we can move. So basically, this is probably the only time in the class where we're going to be considering fluids that don't really move, because you know, a lot of fluid mechanics has to do with fluids that flow, which is, you know, generally what fluids do. But fluids that don't move actually exhibit a lot of really interesting properties too. And to kind of motivate this, you know, if you have some experience deep sea diving, or you've heard about it, or you read about it, or you've seen videos about it, what you know from deep sea diving is that as you go deeper into the ocean, you know, miles underneath the water, you start to feel a lot of pressure, right? Like, you know, you kind of feels like the ocean is kind of like, you know, pushing down on you. At least, you know, I've never been before, but that's you know, the impression that, you know, a lot of those deep sea divers have. Right? And the reason for that is, you know, is because of fluid statics. So we'll see kind of why that is, right? On the opposite side of the spectrum, you know, if you've ever traveled into the mountains, what you know is that as you get higher and higher into the mountains, the air gets thinner, right? It becomes a little bit harder to breathe. And also, you know, if you bring like a bag of potato chips, what you'll notice is that on the ground, you know, your bag of potato chips looks like this, right? But as you go higher and higher into the mountains, you know, the scam that is like Lay's potato chips becomes clear, because you see that, you know, a bag of Lay's potato chips is 90% air, 10% chips. And, you know, as you go further and further up, you know, the bag puffs up more and more and more. Right? And that's, again, due to fluid statics. So, you know, I want you to keep those kind of two physical situations in mind as we go throughout the lesson today, and for the next couple of weeks, because that's kind of the physical intuition that I kind of want you guys to kind of keep hold of. Okay. And so, you know, the other thing I want you guys to keep in mind as we go through this lesson is I want you to remember everything that you've known from before about statics and static equilibrium. Okay? And so, you know, a lot of the like, especially, you know, once we get into the later ones, a lot of the things, a lot of the analysis and a lot of the concepts rely on the concept of all the forces equaling zero. Okay, so you add up all the forces, they equal zero, and you have a stationary object. Okay? Right. So dust off those old free body diagrams, because, you know, we're going to be using them again. So, you know, just because you're in fluids doesn't mean you can escape the free body diagrams, because, you know, those things are extremely important. Okay. So the main driving forces behind these what I call hydrostatic forces is going to be gravity and height. Okay? Okay. And then later on today, that statement will make more sense, but we'll be. I want you to keep in mind, gravity and height; those are kind of the two main main things. Okay. And then the other thing that we're going to be solving for a lot here are pressures. Okay. So let's kind of just remind ourselves what a pressure is. Right. So we touched on it a bit last week when we were going over dimensions, but pressure is a force divided by an area. Okay. Okay. To put this in terms of maybe something that you've covered before in like a solid mechanics class, a pressure is basically it's like a distributed force. So you can say it's a force that's distributed over a 2D area. Okay. 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 So that's all the intro stuff with fluid statics. Okay. So we just to kind of recap, fluid statics, it concerns with fluids that don't move. So we have no fluid flow right now. Our two main driving physical factors are going to be gravity and height, right? And then I also want you to keep in mind what pressure, what the physical interpretation of pressure is, which is just a distributed force, and it's a force that's distributed over a 2D area. Okay. Okay. Are there any questions on this before we move on? Okay. Okay, so let's first talk about the direction of the pressure force, right? And this is summarized in a physical law called Pascal's law. Okay. And so basically what we want to do is we want to answer the question of, say that we have a tub of fluid, okay? So think of this as just like, a big maybe jar of fluid. This might be like, the jacuzzi in your backyard or your swimming pool, right? So if we put an object in here, let's say that we have Illuminati here, right? And the water's not moving, and let's say that this triangle that we have here has a perfect weight and perfect buoyancy, such that it's not moving up or down, okay? At least not due to its own gravity force or any buoyancy that we'll cover later. And so what we want to know is that based on just the shape of this object and based on hydrostatic forces, is the fluid going to push this in a certain direction, or is there kind of a preferred direction that the pressure forces will act, or is there what direction is the pressure force going to push this object? Okay, so that's the question that we want to answer kind of in this first section. Okay, and so to do that, let's take this triangle and let me draw it a little bit better and blow it up. Okay. And so say that we have this triangle object and it's suspended in fluid. Okay. Okay. And we're going to assume for a second that, let's assume that the gravity forces and the buoyancy forces cancel out. So this object's not sinking in the water and it's not floating to the top. So, in terms of height, it's staying kind of in the same height. Okay. And so because this we'll call it a wedge, because this wedge is suspended in fluid, then what's going to happen is that its pressure forces are going to develop on every surface. Okay. And so let's say that we have a pressure force this way. We'll call this PS. Okay. We have a pressure force on this surface. We'll call it PY. Okay. And then we have a pressure force on this surface, which we'll call PX. Okay. And then let's give our triangle some dimensions. So let's say that the height of this triangle, we'll say that this is, the height of this triangle is delta Y. Okay. Let's say that the width of our triangle is delta X. Okay. And then the length of the hypotenuse of the triangle will be delta S. Okay. Okay. And so we have a, we basically have a 2D triangle here where, we have the length of every single side. But, because, we're 3D boys and girls living in a 3D world, let's give this triangle some depth too. Okay. So let's say that going into the page, our triangle has a depth of delta Z. Okay. Okay. And so basically, what that looks like is something like this. Okay. So we have a wedge. It looks like this. Okay. And then this length right here is delta Z. Okay. So think of just like a wedge of cheese, and then the cheese has a depth into the page of delta Z. Okay. Right. So we have our three-dimensional wedge here, and we have our pressure forces. And so what we want to do is we want to take these pressures and then compute a force that's going to be acting on each side of the triangle. Okay. And then once we compute those forces, we're going to add them all up in static equilibrium. Okay. And then we'll use that to determine, what these pressure forces are. Okay. And our triangle has an angle theta. Okay. All right. Are there any questions on this before I move on to the next page? I know it's a lot of symbols and stuff, but it's all going to make, hopefully it'll all start making sense on the next page. Okay. 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 So now that we have our wedge and all the pressures that are on it, let's compute the forces from the pressures. Okay. And so this is something you'll be doing quite a lot, especially once we get into the kind of the later sections of fluid statics. So I want to take some time just to kind of hopefully something that you intuitively know. Okay. So remember what a pressure is. So a pressure is a force that's distributed over an area. Okay. So another way you can say, you can express this is that pressure is equal to force over area. Okay. And so if we want to take this expression and we want to solve for force, okay, all we have to do is just multiply both sides by area. Okay. So we have pressure times area is equal to force. Okay. Because as you know, when we do static equilibrium problems and we want to solve for the forces, we know that we have to sum up all the forces and make sure they equal to zero. So we can't just sum up all the pressures and make sure they equal to zero. We have to sum up forces. So in order to compute the forces on each side of our wedge, we're going to need to multiply by area. Okay. Okay. And so if we go back to the previous page, we can see that each of the pressures that we have here, they're acting on a face, right? So this PX right here is acting on this vertical face. This PY right here is acting on this horizontal face. And this PS right here is acting on the hypotenuse face, okay? And so in order to compute the corresponding forces on each of those faces, we're going to take the pressure and then multiply it by the area of that face, okay? So let's go ahead and do that. Okay. So first, let's do the vertical face, which is this guy right here. Okay. So on the vertical face, we have a pressure of Px. Okay. So we'll call this F1. Okay. So F1 on the vertical face is going to be Px. Okay. So that's our pressure. And so now we need to multiply by the area of that face. And so the area of that face is given by delta y, delta z. Okay. And so remember, delta y is the height of our triangle, and then delta z is the depth into the page. So if we multiply those two, we basically have like a rectangle. Then that's going to be the area of that face. Okay. Okay. All right. So let's do the force on the bottom part of the wedge. Okay. So on the bottom part of the wedge, we have a pressure of Py, P sub y. Right. So let's go ahead and put P sub y. Okay. And then we're going to multiply by the area of that face. And so the area of that face is given by its length. So we have delta x. And then we're going to multiply by the depth. So we have delta x, delta z. Okay. Oops. Okay. And then finally, we have our hypotenuse face. So that's the face up here. Okay. So on the hypotenuse face, we have a pressure of P sub s. So let's go ahead and add that guy in. Okay. And then the area of that face will be the length of that face, which is delta s, delta z. Okay. Right. And so what we can do now is that now that we have these forces computed, we can go ahead and replace the pressures with these forces. Okay. And then from those forces, we can then do a sum of the forces. So we can basically sum up the forces in the x direction, sum of the forces in the y direction. Okay. All right, any questions on this? Does it make sense how we computed the forces from the pressures on our cheese wedge? Yeah. All right, so the question is, what is PS? So PS is the pressure that's on our hypotenuse face. So we said that, you know, on our wedge, we have a pressure that's acting on every side of our wedge. So PS is just the pressure that's acting on the hypotenuse face. Yeah.
Professor, you said this is just a two-dimensional, right? So like there's no pressure like on the Z plane, if that makes sense, like on the face that's going into the page.
Yeah. So so we're going to assume that the pressure that's acting on this face right here, you know, going into the page, and the one that's coming on from the other side, those are basically going to be canceling out from each other. But normally there is that pressure force, but we're just going to assume that it's that they just cancel out basically. Yeah.
Okay, thank you. That makes sense.
Mm-hmm. Okay, so the question is, can I explain how I got F1 again? Absolutely, I can. Okay. So F1 is going to be the force that's going to be on this horizontal, or on this vertical face right here. Okay. And so in order to compute that, we're going to take the pressure that's on the face. So the pressure on that face is P sub x. So that's the pressure, you know, in the x direction. Okay. And then we're going to multiply by the area of that face. So the area of that face will be the height. So the height here is delta y, we can see. Okay. And then we're going to multiply it by delta z, which is the depth going into the page. Okay? So we have p sub x times delta y times delta z. Yeah. So it's the pressure multiplied by the area. And it's the same thing for all the other forces. All right. Any other questions on this before we move on?
Can I get a refresher as to how you get the area out of this triangle? Like you're just multiplying the length times the depth?
Exactly. Yep. Yep. So I'm just taking the length of the side multiplied by the depth. So you can see all of them have delta z because delta z is kind of the depth into that page.
Okay. It's because I can see myself making the mistake of going with the area of the triangle formula being half base times height, right?
Yeah, yeah. So that would be the area of kind of this frontal area right here. So someone asked the question of, it's are we not considering the pressure forces that go in the z direction? So if we wanted to compute the pressure force, and you can't really see it, but like the pressure force that's like going into the page like this into the triangle, then you would do 1/2 base times height, because that's the area of kind of this frontal part of the triangle right here. But we're not considering those. We're basically assuming that those guys are going to cancel out.
Okay.
Yeah, the thing you have to keep in mind is that this wedge is kind of 3 dimensions. So it kind of looks like this guy right here. So it's a wedge. So we're looking at all the pressure forces on kind of the lateral surfaces of the wedge.
Okay, so just this wedge is only in 3D. So unless stated that it's in 3-dimensional, that's when we utilize that method?
Yeah, yeah. Okay. Yeah, and I'll be clear. So any problems that occur. So usually I think that the thing that's kind of confusing about fluid statics is that we're considering all 3-dimensional objects, but all the drawings are in 2 dimensions. Just because in 2 dimensions it's kind of easiest to see the directions of all the forces, and it helps with artistically challenged people like me as well to kind of draw a picture. So one thing that you can assume in this whole unit is that the pictures are going to be in 2 dimensions, but there's an additional dimension that's going into the page, and that's the depth. Yeah.
Okay. Thank you.
Okay. So let's take all these forces here, and then let's apply them on the triangle and see what they look like. Okay. Because ultimately what we want is we want to be able to sum up all the forces, right? So we have, we're basically making our free body diagram right now. And then from there, we can do the sum of the forces in the x direction, sum of the forces in the y direction. Okay. So let's draw our wedge again. Okay. So again, I'm drawing a 2-dimensional wedge, but there's an additional dimension into the page. Okay. And so first, let's draw F1. Okay. So F1 is going in this direction. Okay. And so the magnitude of F1, as we computed on the previous page, is P sub x delta y delta z. Okay. Next, let's draw F2. So F2 is P sub y delta x delta z. Okay. Okay. And finally, we'll draw F3. So that's P sub s delta z. Okay. Okay. So now we have forces, right? Okay. And so now that we have forces, what we can do is we can sum them up in each direction. Okay. And so before we do that, because we have a force here that's kind of slanted, let's go ahead and break this guy up into components. Okay, so by geometry rules, we know that the angle, this angle right here with the vertical is the same as this angle right here. Okay, and so what we can do is we can break this F3 up into its x component and its y component. Okay. Okay, so if we sum up the forces in the x and y, so let's go ahead and do that. So we have sum of all the forces in the x direction. For some reason, my iPad thinks like this weird part of my pinky is the stylus. So sometimes I'll try to write something and my pinky will say nah. Okay, so let's sum up all the forces in the x direction. So in the x direction, we have this F1 that's going horizontally to the right. So let's go ahead and write that, guy. So we have Px, delta y, delta z, okay? And so that's this guy right here, right? And so since that guy is going completely horizontal, then we can just drop that guy right in, okay? And then next we have a horizontal component that's coming from F3, right? So since F3 is pointed at an angle, it has one component, it has some component in the x direction, okay? And so that's going to be PS, delta z, or delta s, delta z, sine theta, okay? And all of that is going to be equal to 0, because remember, we're in a static equilibrium here, okay? So remember, we add this sine theta here just to get the x component of that F3 we have up there. Okay, so that's the sum of all the forces in the x direction. So let's do the sum of the forces in the y. Okay, so first we have F2. So F2 is given by Py delta x delta z. So that's just this guy right here, right? And so since that guy is pointing vertically up, we can just take that as the y component. Okay. Right. And then we also need to add the component from F3. So the y component F3 is going to be PS delta s delta z cosine theta. Okay.
Professor, real quick, when you're adding up or breaking up your third force on the hypotenuse into x and y components, you're taking the angle from the force itself, not the angle of the block.
It's the same angle. So this we know that this angle on the block here is theta, and then because this force right here is perpendicular to this face, right? Then if we draw a vertical line here, then this is going to be the same. It's going to be the same angle because this right here is this down here right here is a horizontal line, right? And so since this guy is perpendicular to that, if we draw a vertical line here, then this guy would be the same angle right there. So it's the same angle just because of the geometry of the situation.
All right, I got you.
Yeah. Mm-hmm. All right. And so before we I open it up and we turn the page, let's first note that every single expression here has a delta z, right? So we have a delta z, right? And so since we have a delta z here, we can pull it out, and then we can also cancel it because on the right side of the equation is just 0. So we're basically just going to cancel this delta z, and we're going to do the same thing down here. Okay. Right. So that kind of simplifies our expression a little bit right there. Okay. All right. And then one other thing that we'll do that I'll write the formula for here, but I'll apply it over there, is we can use the actual geometry of the triangle itself to kind of simplify our expression. Okay. So remember the height of this triangle here is delta y. The width of the triangle here is delta x. And then the length of the hypotenuse here is delta s. Okay. And so we can use this angle here and to kind of help us relate the lengths of the sides of the triangle. Okay. And so particular, one thing we can do is we can say that delta y is equal to the hypotenuse delta s times sine theta. Okay. And then delta x will be delta s cosine of theta. Okay. And so what we can do is we can plug these guys in up there, and this will help us simplify our expression even more. Okay. All right. Are there any questions on this page on summing up the forces? All right. So the question is, why was dz zeroed? So dz was zeroed because it was a common factor in basically all the terms here. And so what I did basically was I factored all of it out, and then I divided both sides by delta z. But since we have a 0 on this side of the equation, because we're at a static equilibrium situation, when we divide by delta z will cancel on the left-hand side of the equation, and then it will cancel out because we're just doing 0 divided by something. Mm-hmm. All right, any other questions on this? Okay. So let's go ahead and make those substitutions that I said on the other side. So we're going to plug in for delta y and for delta x. Okay. So first, let's do some of the forces in the x direction, right? And so if we plug in the expression from before, we'll have px, and instead of delta x, we'll have delta s sine theta, okay, minus ps delta s sine theta, okay, and all that's going to be equal to 0, okay. And before I go to some of the forces in the y direction, let's go ahead and simplify this guy. And so since both of these terms here have a delta s sine theta, we can go ahead and factor those guys out. So we have delta s sine theta, okay, px minus ps, okay, is equal to 0. Right? And so just like we did with delta z on the previous page, we can go ahead and cancel this guy out by dividing both sides. Okay, so we're going to divide by delta s sine theta, divide by delta s sine theta. Okay, and so this guy's going to cancel out, and then the almighty 0 is going to cancel out this guy too, right? 0 is one of those numbers in math that are all powerful, so there's not many things that can win against 0, only infinity. Okay, and so what we get in the end is px minus ps is equal to 0. Okay, if we add ps to both sides, what we get is px is equal to ps. Okay. Right. Okay. And so what this result tells us basically is that, we started with this kind of arbitrary triangle where, we've said that, we know that there's going to be pressure forces that are acting on each side. We just didn't know what those pressure forces were, okay, or what the magnitude of those pressures were, right? And so through this kind of derivation here, what we found is that the pressure that acts on the horizontal face of our wedge is going to be the exact same as the pressure that's going to be acting on the top side of the wedge. Okay? So it seems like a very simple result, but it's something that's going to be really, really powerful. Okay, and so let's kind of finish this up. So let's do the sum of the forces in the y direction. Okay? So we have py, and then we subbed in for delta x. We sub in for delta x. We get delta s cosine theta. Okay. And then we subtract ps, delta s cosine theta, and then all that's equal to 0. So we can do the same thing here. So we have a delta s cosine theta on both sides, on both terms here. So we can do the same thing. We factor out, we divide by both sides, and they cancel out. Okay. So I'm just gonna skip those steps just because I've showed them up here. And then what we get is py minus ps is equal to 0. And then we get Py is equal to Ps. Okay. Right. And so what this result tells us is that the pressure that's on the bottom of our wedge is the same as the pressure that's on the hypotenuse. Okay. And so by transitive property, we can see that Px is equal to Ps, Py is equal to Ps, right? And so by transitive property, we can also say that Py is equal to Px. Okay. So all the pressures are the same. Okay. Okay. And so remember, you know, why we went through this kind of long, really long exercise, right? And so we wanted to determine, you know, is there a preferred direction, or does the pressure kind of lean towards a certain way in a fluid? Okay. And so what we can see here is that, you know, we found that all the pressures on every side of our wedge are the same, right? And so what we can conclude is going to be on the next page. So I'll say, you know, so before I go to the next page, are there any questions on this page and kind of, you know, the end of this this proof? Okay. So the question is that because pressure is depth dependent? So yes, that is ultimately the answer. But you know, we'll get to that kind of on the in a bit. But that's ultimately the answer right there. Okay. So there's a question. So you have a question on the previous page. So let me go back there. Okay. So go ahead. What's your question? So how did I get dy is equal to ds sine theta? So that's just from the geometry of the triangle itself, right? So because the triangle has a, so let's do this side, right? So because the triangle has a height of dy, and then the hypotenuse length is ds, right? So hopefully everyone knows their SOHCAHTOA. And so what we can say is that sine theta is equal to the opposite side being delta y, all over the hypotenuse, delta s, okay? So sine theta is equal to the ratio of the opposite side divided by the length of the hypotenuse. And so by solving for delta y, we move delta s onto this side, we can get delta y is equal to delta s times sine theta. Mm-hmm. Yeah. Yeah, so we're kind of pulling in a little bit from everywhere today. So we're pulling in from your statics class, from geometry, triangle, SOHCAHTOA. So you know, usually I don't like to do kind of lengthy derivations like this, but I think this one is kind of a good refresher of so many different things that it's I think it's kind of a good exercise to kind of remind you of a lot of these things. Yeah. Mm-hmm.
Professor?
Yeah. Mm-hmm.
Would anything change if we say the wedge was not oriented the way it is? So, you know, say if it was like on its side or something, and the area wasn't actual like a square, or it wasn't length times width. It was like 1/2 times the base times height. Would that change anything?
Yeah, that's a great question. So, you know, we did this derivation on kind of a very specific wedge, but you know, just this result that we got, where the pressure is equal on all sides, we can say that this result is going to generalize to basically any size or any shape object as well. So it doesn't really matter, yeah, what size or shape of the object. We did it for a wedge just because the wedge is kind of simple to do. But this result that we got here, which is, you know, all the pressures are the same, you know, we can we can extend that to just any size, shape, object that you can imagine. Mm-hmm.
Okay, thank you.
Mm-hmm. Okay, and so from here we can go ahead and state Pascal's law. So Pascal studied this exact thing. So he went through a very kind of similar mind exercise, and he did experiments to kind of verify this. Right? And so what Pascal's law says that pressure at a point in a fluid at rest is independent of direction. Okay. As long as shearing forces are not present. Okay. And so, you know, what that last point in there is basically just emphasizing the fact that, you know, we have to have a fluid at rest. Okay. And so if there's some kind of fluid, if there's some kind of moving fluid going on, like say you're in the ocean and there's some currents and there's some waves that are kind of pushing you around, then this is not necessarily true because, you know, whenever you have fluid motion, you're going to have some differences in pressure. But you know, we're not going to worry about that for right now. So, you know, we're just going to be concerned about fluids at rest. So for fluids at rest, no motion at all, then the pressure is independent of direction. So you're going to have pressure forces in every direction, and they're all going to be the same. Okay. And so visually, it looks something like this, right? So let's say that we have our, you know, bathtub, jacuzzi, swimming pool, whatever, right? And say that we consider a point right here. Okay. And so what's going to happen at this point is that you're going to have pressure forces, okay? And they're going to be acting in all directions, and they're going to be acting in all directions equally, right? So the pressure is independent of direction. It's just going to be pushing it all around, right? And if you think intuitively, you know, this kind of makes sense. Like you drop a marble in a fluid, and let's say the marble floats, right? The fluid just by itself, just by, you know, the fact that there's a still fluid, it doesn't push the marble in one direction or the other. I mean, the marble might sink just because of its weight, but, you know, the fluid doesn't push it to the left or doesn't push it to the right or doesn't push it diagonally up to the left, right? So pressure, you know, it acts equally basically in all directions on a point, okay? So another way that we can say that is that pressure has no preferred direction. So it was a very kind of lengthy way to kind of state something that's, you know, intuitively kind of obvious. But again, you know, the reason we kind of went through that whole proof is to kind of jog your guys' memory on like free body diagrams, geometry, because it's all that we're going to be using a lot over the next 2 weeks. Okay. All right, are there any questions on Pascal's law? So the question is, pressure has no direction only in hydrostatics. That's correct. Yeah. So once we start to put a motion into the fluid, then you know, pressure is going to be, there's going to be some gradients in pressure, or there's going to be some differences in pressure that we need to consider. So this Pascal's law right here is only valid for fluids at rest. So this is going to be fluid statics, hydrostatic situations.
Professor, just to clarify, hydrostatics, hydro. Can you explain just the word comes from hydro? Is that just water-based or? Yeah,
so hydro specifically, whenever you see it in a word, that specifically means water. So there's hydrostatic, so that's water at rest. So kind of the more general term would be fluid statics, which is just any fluid at rest.
Okay.
Yeah, so it could be, you know, salt water, it could be air, it could be stuff like that. So hydrostatics specifically refers to water, which for a lot of cases, you know, this is and that's what this kind of theory is applied to. But it also applies to, but you know, this is more general for fluid statics, which is any kind of fluid. Mm-hmm.
Okay, thank you.
Mm-hmm. All right. Okay, so that's Pascal's law. So it's intuitively, you know, hopefully it's something that makes sense, but it's something that's, you know, really important for fluid statics. Okay. So the other really important concept that we need to go over is how does pressure actually vary in a fluid? So this goes back to, I think, a comment that someone made earlier about, you know, pressure depending on depth. And so we'll see that kind of, we'll kind of see why that happens here. Okay. And so basically what we want to answer here is say that we have our, you know, our tub, right? We'll call this P2 actually. Okay. And so say that we have 2 points. So say that we have a, a point up here near the surface, and then we have a point down here near the bottom. And what we want to say is that, how does the pressure vary between these 2 points? Okay. Because we've just established with Pascal's law, how does the direction of pressure vary at a single point? But now we're ready to compare between 2 different points. So if we have 2 different points in a fluid, how does the pressure compare between those 2 points? Okay. And in particular, what we want is how does the pressure magnitude vary, or the value of the pressure. Okay. And so if you look in the lecture notes, and if you look in the textbook, what you'll see is that there's another very lengthy, mathy, free body diagram-y, derivation for this. So, I think, 1 is enough per day. Thinking about this morning, I think, another way that we can describe this is kind of a little bit more intuitively, okay? And this is, I think, kind of a much more central and a much more core concept to fluid statics as a whole. So I think, with these kind of concepts, I think it's better to explain it intuitively rather than through a bunch of math and a bunch of, proofs that, you might not remember the details of, once you leave the class. Okay? And so to kind of explain, how a pressure varies, I want to kind of bring your attention back to something we mentioned at the very beginning of class today, where hydrostatics depends a lot on gravity and it depends a lot on height. Okay. And so let's take kind of a mental experiment or a mental situation. Okay. So let's say that we have a person. Okay. He's a happy person, although because my stylus is being weird, he looks like he has a black eye. Okay. Let's draw his arms a little bit bigger. Okay. And so let's say that this person's participating in a strongman competition. Okay. For some reason, Facebook thinks that I like these videos, so it keeps suggesting videos of really buff guys carrying barrels of sand places. I watched them to their completion, so maybe they're onto something. But it's weird that they just randomly suggested it to me, and they keep suggesting it to me. I mean, they're really cool. I like watching them, but yeah, it's kind of weird. Okay, so let's say that we have our strongman here, and then let's say that we put a slab of concrete on top of his arms like that, okay? But he's strong, so it's okay. He's carrying it just fine, right? And so in order for him to carry this, his arms have to exert a certain amount of force in order to carry it, right? And why is that? His arms have to exert a force because they're supporting the weight of the concrete. Okay. 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 And so let's ramp this up. So let's put another slab of concrete on top. Okay. And so what's going to happen when we put another slab of concrete, right? He's strong enough, so he's not going to fall here. Okay. And so by adding another slab of concrete, what does his arms have to do? His arms have to exert more force because there's more weight for him to support. Okay. And so we can keep adding more, right? And so as we add more and more, we know the arms have to exert more and more force because it's more and more weight for them to support, right? So intuitively, you know, this makes sense, right? The more weight that you have above you, you know, the more force that you have to exert to support that weight, okay? And so let's take this concept and let's apply it to fluids and see how that works, okay? But before we do that, are there any questions on this page before we move on? Okay. So let's let me draw our tub of water again. Okay. And let's draw our 2 points. So we'll say P1 and P2. Okay. And so first, let's look at P1. Okay. And so P1, you can see, is very near the surface. Okay. And so just by nature of being near the surface, it has very little fluid on top of it. Okay. Okay. So if there's very little fluid on top of it, if we kind of connect this back to our strongman example, right? We can say that this is kind of like the situation where you only have maybe like one concrete block on top. Okay. Okay. And so what we can say is that the fluid at P1 is only supporting a very little amount of fluid on top. Okay. So the key here is supporting. Okay. Okay. And so let's compare that to our point P2, where P2 is near the bottom of the tank, right? And so by nature being near the bottom of the tank, you know, it's supporting all the fluids on top. So there's a ton of fluid on top of P2. Okay. Okay. And so if we connect this to the strongman example, this is kind of like where we ended up with just, you know, maybe 5 or 6 or 7, you know, blocks of concrete on top. Okay. Okay. And so another way we can say that is that the fluid at P2 is supporting a ton of fluid on top of it. Okay. Right. And so just like the situation where, you know, we had a ton of concrete blocks on the strongman, you know, the strongman had to exert, you know, a lot more energy and a lot more force in order to support that, right? And so what we can say is that P2 has to exert a lot more force in order to support all the liquid on top of it, okay? And so, you know, the question you might be asking is, you know, how exactly does fluid exert this force? Like how does it's, you know, fluid's not the same as a person, right? So they can't just flex their muscles a lot harder in order for them to support all the fluid on top, right? And so the physical mechanism in which the fluid can actually support the fluid that's on top of it is the pressure, okay? And so just like the strongman, where, you know, we know he has to exert a lot more of his muscles in order to support more of the blocks, what we say that in order for the fluid to support all the fluid on top of it, the pressure has to be higher, okay? Okay. And so what we can basically say is that, you know, the deeper you get into the fluid, or the farther you get below the surface, then the pressure has to increase. And the reason that pressure increases is because, you know, the fluid at the bottom has to support all the fluid at the top, okay? Or in other words, you know, gravity and height are kind of the main determining factors for pressure in a static fluid. And so I'll put an equation on this on the next page. But before we move over there, does this kind of, you know, does this make sense to everyone? Are there any questions on, you know, how we came to this conclusion that pressure is higher at deeper depths than at more shallow ones? Okay. And so you know, let's kind of sum that up again. Okay. And so the formula for this is actually very simple, although it involves a derivative, okay? Okay. And so if we say that y is the direction that goes deeper into the fluid, okay? Y is the vertical direction. Okay. And then this P right here, this P with the ponytail, this is pressure, okay? This is going to be confusing because I'm about to write density rho in the same, in the exact same expression. But just kind of bear with me. Okay. 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 So this P right here, this is pressure. This looks like a P, but it's actually rho. So this is density. Okay. This G right here is gravity. Okay. And then just a shorthand notation, this gamma right here, remember this is specific weight. Okay. Right. And so this equation right here, this says that the rate of change of pressure in a fluid with respect to the vertical direction is equal to negative density times gravity, right? Okay. Or we can say, and since density times gravity is specific weight, where specific weight is the weight of the fluid per volume, okay? We can say that the derivative of pressure with respect to the vertical direction is also equal to minus specific weight as well, okay? So depending on, you know, the numbers that you get in a problem, either I give you density, okay? If I give you density, you have to multiply by gravity. But if I give you specific weight, then you can just use that directly into this formula, okay? And so, you know, this formula is in derivative form. So usually, you know, for practical problems, we integrate this. Okay. And so let me just take just the first part of the equation here. So we have dP dy is equal to minus rho g. Okay. So let me go ahead and integrate this with respect to y. Okay. So remember, when we integrate something, we always have to have a with respect to y. Okay. And so this is probably the more useful form of this equation that we'll use quite often. Okay. Okay. And so if you want to get the difference in pressure between 2 points in a fluid, so we say that P1 minus P2, the way that we're going to do that is we're going to compute minus rho times g multiplied by their height difference. Okay. Okay. So we have a difference in height and we have a difference in pressure. So both of these equations, both the ones that I boxed are valid, but probably the one on the bottom is what we'll practically use more for equations, just because it's, you know, we're comparing two discrete points. Okay. Right?
Professor, so no, we're doing the integration from the vertical, would y1 be with respect to the point one? Point
Yeah.
one? Okay.
Yeah, it can be any 2 points. So as long as, you know, as long as you're consistent in the ordering here. So you have P1 first and Y1 first here, P2 first, or P2 second, and Y2 here. So it doesn't necessarily have to be from the upper point to the lower point. You can do lower point minus upper point, as long as you're consistent in kind of the ordering of the terms in the equation. Yeah. It can be any 2 points that you can pick.
Okay.
All right, any other questions on this? Okay, so we're almost out of time, but I do want to give you 2 more pieces of trivia, you know, before we do an example, which we'll probably do next time. Okay. So 1, notice how, you know, the previous expression only with respect to differences in height. Okay, so if you travel horizontally in a static fluid, you actually won't experience any pressure differences at all. So we can say that pressure does not vary in horizontal direction. Okay. So as long as you're in the same height, you can move, you know, anywhere you want in the horizontal plane, and you're still going to have the same pressure, right? And remember, the reason for that is, you know, the reason pressure becomes a thing is because the pressure develops because of supporting the weight of the fluid above you. So as long as you're in the same height, you're in the same plane, then you're going to see the same pressure because you have the exact same amount of fluid that's above you. Okay. Okay. And so the other thing is that pressure only changes with depth and elevation. Okay. Okay. And so as you go deeper in the fluid, the pressure will increase because it has to support all the fluid on top. Okay. Okay. And the other thing is that, you know, if your fluid is more dense, then this variation is going to be greater. So if you have a fluid that's really dense, you know, you go 1 meter deeper in a fluid that's really dense, you're going to feel a really big increase in pressure. But if you go 1 meter down in a fluid that's not so dense, so say, you know, air, so you basically just walk downstairs in your house, you don't really notice a difference, you know, when you walk, you know, downstairs, you know, even from the top of, like, you know, say the CS building down to the bottom, you don't really feel a difference in air pressure because air is not that dense at all. But if you walk down a 5-story building in like a swimming pool, you know, you really feel that because water is a lot more dense than air. Okay? And so this variation depends a lot on density. Okay, are there any final questions on this? Okay, so we're out of time today. So so thank you everyone for tuning in. So I know we did kind of a lot of derivations and a lot of conceptual stuff. So next time we're going to do some examples that kind of, you know, illustrate all of these things. So thank you guys for your patience today, and thank you for tuning in. And I will see you guys on Wednesday. Okay. You'll go back a page. Yes, I can. All right, so I'll stick around for a bit if there's any questions, but if not, you guys are free to go. Okay.
Thank you,
Thanks,
Professor.
Professor.
Thanks, Professor.
Thanks, everybody. Have a good day.
You too. Thanks.
All right, so question. Was buoyancy considered during this fluid stack? So we are going to do buoyancy, but buoyancy is kind of its own thing. So right now we're concentrating just on pressures, but we'll do buoyancy probably next week. Yeah, so it is considered part of fluid statics, just a different part of it. Yeah, so we'll learn about hot air balloons and Archimedes principles and all that good stuff. All right, Ryan, do you have any more questions? Okay, so I'm going to close the call. If you have any more questions, I have office hours right after this.